All right, so I'm just going to briefly talk about radioactivity. So radioactivity is the process in which a heavy nucleus, which means a nucleus which has a lot of protons and neutrons, spontaneously decays into a lighter nucleus in a specific way. So that decay just means transformation here. Decay just means uh, transforms into a lighter nucleus in a very specific way. So this transformation can happen in a couple of different ways. One method, just which I'm using just as an example, is that suppose you have a very large number of you have a nucleus with a very large number of protons and neutrons. So I just mean to have lots of p's and n's, not just the number I've written over here. So there's plenty of protons and neutrons inside this nucleus. It might happen that a small unit of this nucleus might just leave. So one example would be these two protons and these two neutrons might just spontaneously leave this nucleus and leave behind a nucleus which is short two protons and two neutrons. And this unit that just took off, which consists of two protons and two neutrons, is what kind of nucleus is this? So since this has two protons in it, it's obviously a helium nucleus. The simplest nucleus is hydrogen, which has one proton, and the second element in the periodic table, the second simplest nucleus, is helium, that has two protons. So this large nucleus just shot out a helium nucleus and transformed into another nucleus which is short two protons and two neutrons. So this is one way in which a heavy nucleus can transform into a lighter nucleus. This particular type of process is called alpha decay. Decay, remember, doesn't have anything to do with the English meaning of the word decay, it just means transformation. This is called alpha decay. Just because this particle, before people knew that it was a helium nucleus, they called it an alpha particle. They knew some particle is coming out of the nucleus, but they didn't know what it was. And so it was called an alpha particle, which we now know is a helium nucleus. So the point is that certain heavy nuclei can spontaneously turn into lighter nuclei, and I showed you one method in which that might happen by shooting out an alpha particle. Okay, now this happens at a very specific rate, and the rate is determined by the number called the half-life. So we are not going to get into the details of the half-life very much, but if you happen to know the half-life of the decay of a particular element, then you can figure out how much of that element is going to decay in any amount of time, like how much of it is going to decay in 1,000 years or in 5,000 years. That's not hard to figure out if you happen to know the half-life, and the half-life is not hard to measure either. Okay, so why is this useful in astronomy? Well, it provides you a very um, easy way or a very clean way of figuring out the age of different objects or different rocks, for instance. So let's look at this slide over here. So let's take the element uranium. You can see the mass number of uranium, it's 238. Mass number means the number of protons and neutrons in each uranium nucleus. And so that's 238. So you can see that's a very, very heavy nucleus. So this uranium nucleus decays into lead. That is the result of the transformation, and it's not just one transformation that happens. So it's not just one alpha particle that it shoots off. There's a series of transformations that happen, and ultimately it turns into lead, which has a much lighter, which is a much lighter nucleus. You can see that the atomic mass of lead is only 206, whereas the atomic mass of uranium was 238. So it turned into a much lighter nucleus. Um, and not all of this uranium has transformed into lead. You can see that about half of it has transformed into lead. The rest is yet to transform or decay. So by so suppose you are a geologist and you find this rock which is about half lead and half uranium, and you happen to know that uranium transforms into lead through radioactivity. Then by measuring how much of that block is lead now, and knowing that once upon a time it used to be all uranium, but as a result of radioactive decay, it's half of it has turned into lead. And if you also know the rate at which uranium decays, you can figure out how old this rock is. So radioactivity provides you a way of figuring out the ages of different things. So you just want to find out how much daughter element is there. Daughter is the decay result when the nucleus transforms. The resulting nucleus is called the daughter. So how much of it is daughter and how much of it is parent? Parent is the original nucleus. So here lead would be the daughter and uranium would be the parent. So how much of it is daughter and how much of it is parent? You can figure out how old the rock was. So very briefly, that is how you can use radioactivity to find out the ages of things. And in astronomy, this is obviously very important. We can figure out the ages of rocks on our planet, and that gives us an idea of how old those rocks were. And it also helps us come up with estimates of how old the Earth is. We can figure out the ages of asteroids which hit the Earth, meteoroids and asteroids. We can also figure out the ages of fossils using the same principle. That is called radiocarbon dating, and I'm not going to get into the details of that. But the in principle, it's very similar to what we discussed. All right, so you are not really responsible for the details of alpha decay and beta decay, but since I just mentioned alpha decay, I'll just show you this slide. So this is the heavy nucleus. This is plutonium, and it's got a mass number of 240, atomic number of 94. Atomic number is the number of protons, mass number is the number of protons plus neutrons. So you can see that this is a very heavy nucleus with 94 protons and 246 total number of protons and neutrons. So this gives off an alpha particle. As we just discussed, an alpha particle is a nucleus of helium which consists of 2 protons and 2 neutrons. And so you're left with another heavy nucleus which is a little bit lighter than the original one. So since 4 protons left, the mass number has gone down from 240 to 236, because 240 minus 4 is 236. And since the alpha particle consisted of 2 protons, so that means 2 protons have left in the alpha particle. So the atomic number, which is the number of protons, has gone from 94 to 92. So this is the parent element, plutonium, and this is the daughter element. Okay, so that's just one example of radioactivity. There are two other examples of two other types of radioactivity, which I'm not going to go into. All right, and we can skip this problem. Okay, so you just need to have some understanding of what radioactivity is, because we'll often talk about using radioactivity to find the ages of different things. So hopefully that is clear. All right. Okay, the next thing that we're going to talk about is the continental drift hypothesis. So the idea here is that the continents that we see on our planet now were not all in their same locations that you see them now. They were not always in the same locations that you see them at now. In fact, it is believed that once upon a time, all the continents were in one gigantic landmass, which was called Pangaea, and the rest of the surface of the Earth was one huge gigantic ocean, which is named the Tethys Sea. So there was only one continent. It was called Pangaea, right? And then this continent broke up and into various pieces, and those pieces are what we call what we see as the continents that we have today. Okay. So this supercontinent was called Pangaea, consisting of all the world's land masses. And about 200 million years ago, it began to fragment into smaller masses. And those smaller masses, or those continental blocks, then drifted to their current locations over a span of millions of years. So this idea, which sounds crazy if you think about it, was put forward by Alfred Wegener in 1915. And as you would expect, there was tremendous opposition to this idea because it was very, very difficult for uh, people to believe that this can be true. But Wegener had studied this in a lot of detail, and he had several pieces of evidence which seemed to indicate that this idea is true. So, what I'm going to do now is go over the evidence that Wegener had back in his time, 1915, which convinced him that this idea of continental drift is correct. Okay, so this slide just shows you the process of the continental drift happening. So this is what Pangaea was 200 million years ago. And here you can see that it's beginning to break up. It's broken up some more, broken up some more, and some more. And now this is what the world looks like. So this is kind of what actually happened with Pangaea and how it broke up. All right, so what evidence did Wegener have which convinced him that the continental drift hypothesis is correct? The first piece of evidence that Wegener considered was that there is a remarkable similarity between the coastlines on the opposite sides of the Atlantic. So look at South America and Africa. They almost perfectly fit together, like two pieces in a jigsaw puzzle, right? Now, this piece of evidence, all of the things that Wegener put forward, all the ideas that he put forward as evidence for the continental drift hypothesis were challenged by other scientists of his time. So other scientists of his time challenged this idea, saying that the shapes of the coastlines really mean nothing because they keep on changing, right? So the shapes of the coastlines are not fixed, and so the fact that they seem to be fitting together means nothing because they keep on changing. Now, this criticism on the face of it seems sound, but actually it's not correct, and that is something that we know now. So later on, scientists found out that the better thing to compare rather than the coastline itself is the continental shelf. So what is the continental shelf? So you know that suppose you're at the shore of the ocean right here, and you can see the waves sort of coming in, and this is the water. So if you keep stepping into the water, it's going to get deeper and deeper and deeper and deeper. You know, like maybe over here it's deeper than this person, and it'll gradually keep getting deeper and deeper, and then all of a sudden it'll just drop off, right? And so then you have ocean. So this point is the continental shelf. This is where the continent truly ends. It's not over here where the water meets the shore. The continent truly ends right here, and that's called the continental shelf. So if you look at the continental shelves, and which can only be photographed from space, if you look at the continental shelves, you find that they fit very, very well. So you don't even have to look at the actual shorelines. The better thing to look at is the continental shelves, and the continental shelves fit almost perfectly like pieces in a jigsaw puzzle. So Wegener was absolutely correct that the shapes of the continent seem like they were once together. Right? All right. Another piece of evidence that Wegener put forward was that there are, if you look at fossil remains, there are certain identical fossil organisms which are found um, in both South America and Africa. So I'll give you three examples of that. One of them is this um, Mesosaurus. So that's a crocodile like freshwater reptile. So so he's a freshwater reptile. So he's not he's not some he cannot swim in the ocean. So how is it that you find Mesosaurus fossils in South America and also in Africa? Uh, there is no way a Mesosaurus could swim 5,000 kilometers of open ocean to go from South America to Africa, right? So how can you possibly have Mesosaurus fossils in both South America and Africa unless these two regions were the same region? And then there are another example is this plant, the Glossopteris. So the Glossopteris is a um, is a tree which gives off which disperses its seeds. It has these heavy seeds which just fall pretty close by near the tree. So how can Glossopteris propagate across 5,000 kilometers of ocean? Doesn't make sense. Uh, the third example would be Lystrosaurus, which is a land-dwelling mammal over here. So yeah, so the Lystrosaurus is a land-dwelling mammal. So he doesn't even swim. So how could you find Lystrosaurus fossils on both sides of the Atlantic in South America and Africa unless these two were part of the same continent? So these identical fossil organisms found on both South America and Africa were was another piece of evidence which convinced Wegener that these two continents were joined at some point. The third piece of evidence that Wegener considered was that uh, there are certain mountain belts which seem to terminate on one coastline and then reappear on land masses across the ocean. So one example would be the Appalachian Mountains. So you have the Appalachian Mountains in North America, as you know, but the Appalachian Mount, but um, they yeah, so they you have them in North America. You have some of them in Newfoundland, Canada, and then you have identical mountains in the British Isles and also in Scandinavia. They are very, very similar to the Appalachian Mountains that you see in North America. And so it seems that all of this was just one mountain range at some point, but then they got separated. Okay. All right. Another piece of evidence that Wegener put forward was that it seems that there was a glacial period which has been dated back to the Paleozoic age, which is 300 million years ago. So 300 million years ago, there was a glacial period in certain regions, and these regions are Southern Africa, South America, Australia, and India. So 300 million years ago, Southern Africa, South America, Australia, and India had a glacial period. Glacial period means that these places were completely covered in uh, uh, under glaciers. So very, very thick sheets of ice covered these entire regions. Um, However, these regions, most of these regions are pretty close to the equator. So I'll just show you where these regions are. So there was a 300 million years ago, there was a glacial period over here, over here, over here, and over here. Now, it's very hard to understand how these regions, which are not that far from the equator, why would these regions be completely covered in ice? Maybe there was a, maybe there was a you might say that maybe the whole world was covered in ice, right? The Earth has gone through a couple of glacial phases. So maybe there was a global glacial phase going on in the Earth. The whole Earth was covered in ice, but that is not true in this case because so it was not a global ice age because there were large tropical swamps lay in the northern hemisphere. So there was, at the same time, we have evidence that this region was a very large tropical forest. These regions were large tropical forests. Um, so it was clearly not a global ice age. So how would you explain that there was so much ice in these regions 300 million years ago? The explanation is that these regions were all part of Pangaea, um, which happened to be where Antarctica is right now. So this is what Pangaea looked like, and these regions were near the south pole of the earth, and so they were covered in ice at that time. And these regions, North America, parts of the Middle East and Europe, at that time happened to be near the equator, and so they had lush forests. Interestingly, what happened to these forests? These forests eventually went underground and turned into coal. Okay, all right. So hopefully this point is clear that 300 million years ago there were uh, certain regions which are now close to the equator that seem to have had a global that seem to have uh, been completely covered in ice, and it's very hard to explain that unless you assume that they were all parts of the supercontinent Pangaea, and these regions happen to be close to the south pole, um, and that is why they were all covered in ice 300 million years ago. All right, so these were the different pieces of evidence that convinced Wegener that the continental drift hypothesis is correct. Now, this question of continental drift is no longer in doubt today. Scientists have plenty of evidence that this actually is going on, and not only that, we can tell that the continents are moving. We can actually measure their movements pretty accurately. We are now going to try to understand why this continental drift happens. So why do the continents move around? All right. So we had talked about the structure of the earth, and just to remind you, the different layers of the earth were, you had the core, which consists of a solid core and a liquid core. I'm just drawing one circle for the core. And then you had the mantle, right? Mantle was made up of rocks, and then you had the very, very thin crust, which I'm drawing over here like this. So the crust is the lightest part, is the least dense part of the earth. Okay, so this is the crust, and this is the mantle, and this is the core. Actually, it's probably better if I just switch to the Word document when I'm drawing this so I can make different colors. So I'll just draw that again. So this is the earth. Let's say this is the core, and I'm just going to draw the crust of the earth. Remember that the crust is very, very thin in comparison to the mantle and the core. All right, so this is the innermost circle is the core. Then you have the mantle, and this very thin layer is called the crust. All right, the crust consists of the the crust is the part of the earth that we're familiar with. So it makes up the continents and the ocean floor. All right, now it turns out that the crust, uh, together with the uppermost layer of the mantle, is it makes up a thin, a strong rigid layer, which is called the lithosphere. So the lithosphere consists of all the crust and a part of the mantle, the uppermost part of the mantle. This is called the lithosphere. So this region is called the lithosphere. So, and it's rigid, like the shell of an egg. So the lithosphere is this rigid outer layer of the Earth, which consists of the crust and the uppermost part of the mantle, right? So that's called the lithosphere. And then the lithosphere also is not completely intact. It's broken up into segments, and those segments are called plates, right? So just imagine that you have an egg. The outer shell of the egg would be the lithosphere. Now just imagine that you've lightly hit the egg with a spoon, and so you can see that the shell is cracked. So that's what the Earth's lithosphere looks like. It's not completely intact, but it's broken up into pieces, and those pieces are called plates or tectonic plates. Okay. Now, the lithosphere is thinnest in the oceans. It's about 100 kilometers thick, and it can be a little bit thicker underneath the continents. It's about 200 to 300 kilometers thick underneath the continents. All right, so hopefully the lithosphere is clear to all of you. Now, the lithosphere lies above a weak region in the mantle called the asthenosphere. So I had drawn the lithosphere over here, this purple circle. Now, just underneath the lithosphere, you have a weak region of the mantle, which I'll draw with this orange circle. So this, and I'm just also going to shade it. So this region of the mantle is called the asthenosphere. So this consists of rocks um, which are soft and and malleable, just like putty, and that is because of the temperature and pressure at which these rocks are. They happen to be a little bit soft and malleable and not completely rigid. So that is the asthenosphere, is this region of semi-solid rock which is directly underneath the lithosphere. Okay. Yeah, and the temperature and pressure in the lithosphere are such that the rocks are very near their melting temperature, and as a result, they can sort of flow around like a custard or a jelly or putty. So they are not rigid. Okay, so as a result of that, the lithosphere can move around on top of the asthenosphere because it's not sitting on something that's completely rigid. It's sitting on this putty-like surface, putty-like rocks underneath it. And so as a result of that, the lithosphere can move around. Okay. Now here is a picture which I found in a different book, which shows the same thing. So the lithosphere is this outermost layer. As you can see, it includes the crust and the mantle. The crust is the crust and the uppermost mantle. The crust is consists of the oceanic crust, which is the part of the crust underneath the oceans, and the continental crust, which is the part of the crust underneath the continents. And so you can see the crust at the very top of this diagram, and then you can also see the upper mantle, which is also a part of the lithosphere. So this whole region is the lithosphere, and it's rigid. And then underneath the lithosphere, you have a region of semi-solid rock, which is the asthenosphere. Okay, so hopefully this is clear to you. So the asthenosphere is directly underneath the lithosphere, and it's a region of semi-solid rock, which is easily deformable and can flow. And then above the asthenosphere, you've got the lithosphere, which consists of which is hard, and it consists of the uppermost mantle and the crust. Okay. All right. So as I mentioned earlier, the lithosphere is not completely intact, but it is broken up into these segments of irregular shapes and sizes, and these segments are called the tectonic plates, or plates for short. So a tectonic plate can include oceans, and it can include continents and the ocean floor. So sometimes people have the misconception that a tectonic plate is probably what we see as the continents today, but that's not quite true. So you can see that this tectonic plate right here, which is called the North American plate, consists of North America and part of the Atlantic Ocean as well. So the and then this tectonic plate called the South American plate has consists of most of the continent of South America and also a part of the Atlantic Ocean as well. So the tectonic plates can consist of continents and ocean floor. So it's not just continents. So hopefully the meaning of tectonic plate is clear. So we talked about how the outer layer of the earth is called the lithosphere, and the lithosphere is hard like the shell of an egg, and then the lithosphere is not completely intact. It's broken up into these segments, and these segments are what we call tectonic plates. Now, since the tectonic plates, which are basically the segments of the lithosphere, are sitting on a soft surface, the asthenosphere, they have the freedom to move around a little bit. And so the tectonic plates move relative to each other, but very slowly. They move at a speed of around 5 centimeters per year. And so that is the same speed at which your fingernails grow. So that is the speed at which the tectonic plates move around. So as these tectonic plates move, there are various interactions among their boundaries. So you can have a situation where two tectonic plates move towards each other, and that is called a convergent boundary, where the plates are moving towards each other. You can have a situation where the plates, two tectonic plates, are moving away from each other, and that is called divergent boundaries. And you can also have a situation where the two plates, the boundaries of two tectonic plates are sort of grinding against each other and going in opposite directions. So if this is one plate and this is another plate, this plate might be moving this way and this plate might be moving the other way. And so there might be a lot of friction as the two plates grind past one another. So that is called a transform fault boundary. And in the next video, we will discuss each of these interactions in a little more detail.